dyspsia that actually dilutes the concentration of sodium in your blood plasma level, and then you can have this kind of problem. So salt is important. If you look at history, 6000 BC, in China, in the eastern part of China, people used to harvest salt from this lake. Present day Bulgaria, there was a place, it is still there, it is a archaeological place where you had the, first salt mine. It was like 5400 BC. What is the connection between salt and Bollywood? Many of you have seen this famous, scene from Sholay, the movie. The villain, Gabbar, and his associate, he came back from a raid, and Gabbar says, "Tera kya hoga Kalia?" And Kalia says, "मैंने आपका नमक खाया है सरदार." So Gabbar says, "अब गोली खा." So you see that salt is very important. You just cannot deny, right? So it is also associated to our history, the India's independence movement by M.K. Gandhi, the famous Dandi March. Dandi is here somewhere, whatever. Yeah. And it so happened, when I came back from my postdoctoral training, I came back to join an institute here in Bhavnagar, which is in Gujarat, in this part of the Gujarat, the other side of the Gulf of Bombay. And there I started my independent research career. So today I will be sharing with you my own experience that came to me as a scientist, and I have been asked, actually, it was not my choice to work in this area. I have been asked by the then director of our institute, Dr. Pushpita Ghosh, to work on this project. The project came from Hindustan Lever. As you know that Hindustan Lever, they are in the business of consumable goods. They probably make anything, sell anything that we use every day. And salt is one of them. They came up with this proposal that we want to make salt free-flowing. All of us know that salt, particularly during monsoon season, they kind of cake, It is very difficult to take salt out of your salt dispenser. And they said that there are lots of methods available, which I did not know, because my background was not in salt. They said that they apply all kinds of additives like silica and other things to make salt free-flowing. Free-flowing means, as I said, that if you take a salt dispenser and you just, shake it, salt should come out just like that. It should not cake. It is not only the application that is important in your everyday life, related to food and other things, but suppose if you go to northern part of India, let's say Kashmir or Himachal Pradesh during winter, you have a lot of snow, and salt is used to melt the snow. And in that case, sprinkling salt on a huge surface is very important. And if you do not have the free flow, then you will be using more salt. Okay, it will be not very economical. So that was the problem. But they said that there are many things known, but we want you to look into the problem in a different angle. They said that you have to do something to the salt, modify the shape of the salt so that its flow increases. So that was the problem given to us. And unfortunately or fortunately, my background was in crystallography. Let me tell you this, this is particularly addressed to the student. You see, crystallography means people who practice crystallography, they use X-ray diffraction to solve the structure and analyze the structure. They also grow crystal. But if you say a crystallographer is a crystal growth person, is a mistake. But our director told me that there is only one crystallographer in the institute, and this particular project is related to salt which is crystalline, and therefore you have to take this project. I argued. I said, no, I am not a crystal growth person. This is a completely crystal growth problem. It is nothing to do with crystallography. There is nothing doing. You have to take this project. Otherwise, the institute will lose money. Okay, whatever it is, so I had to accept that, and the journey began. So this is the story I want to share with you. So if you look at the source of salt, there are many sources. One of the sources is sea, but this particular picture is Dead Sea. If you go to Israel, you see, in Israel, this part. This is Dead Sea. Half of Dead Sea is within Israel and half of this is within Jordan. I had the personal, because I did my first postdoc in Israel, so I had the personal opportunity to go to Dead Sea and actually float like this that you can see. Because the salinity of Dead Sea is about 34.2%. So if you don't know swimming, nothing happens. You will float because of the density. And this is the salt crust that you can see. But our main source of salt is sea. And 3.5% salinity is there in the sea. So you have a lot of salt in sea and you can collect salt by harvesting. Harvesting means you have to crystallize it. But salt contains many other, sea water contains many other components other than sodium chloride, which is the major component. It has got magnesium chloride, calcium sulfate, calcium chloride, and a few other traces elements. So there are some process that they do, and this is how it is done. Schematically I have shown here. So they pump water in a reservoir and then allow it to evaporate. By this way, they first take out gypsum, which is calcium sulfate, and then they pump it back to another reservoir, and then finally salt crystals come out, and after that you have to do other purification steps. Some people do crystallization by evaporation, some people do other kinds of crystallization techniques and so on. This is the typical picture of salt harvest. If you go to Bhavnagar area, you will see that there are many of salt farms like this. There are some more pictures, as we can see. Now, is sodium chloride is hygroscopic. We all know that it is hygroscopic, but pure sodium chloride is not hygroscopic. If you take industrial grade sodium chloride, which is more than 99% pure, it will remain as such. Sodium chloride is hygroscopic because when you harvest salt, you have calcium chloride and magnesium chloride as well, and they are hygroscopic, and that makes the sodium chloride hygroscopic. So, answer is no. So, see, this is typically caking of sodium chloride, you see, that we all experience during monsoon season, and it contains calcium chloride and also magnesium chloride, and because of that reason, they become hygroscopic. So, in some way, if you can remove magnesium chloride and calcium chloride, sodium chloride becomes free-flowing, non-hygroscopic, which is industrial grade, 99.99% sodium chloride. But making that quality sodium chloride is not easy, and that's why you can see that industrial grade sodium chlorides is very expensive. So, industry people who generate salt for everyday consumption, they cannot afford to do so because salt, per kilogram will be like 1,000 rupees or so. So nobody can afford to buy such things. So you cannot avoid calcium chloride and magnesium chloride in any way. So you have to find out alternative. So industry, they use silica, as I said, they use precipitated silica to make some kind of coating during crystallization, and that coating helps this crystal grain not to be hygroscopic. This is one of the way of making sodium chloride free flowing. So this is what I said. Hindustan Lever came to us with few questions. There are many other questions, but main question was this: how to prevent caking and improve flow properties by modifying its habit. So how you can do that? If you consider these blocks, sodium chloride, we all know that they are cubic. So if you take few cubes and if you roll on the floor, will it roll? It will not, because of its shape. But instead, if you take this what they call marble, we used to play when we were child, the marble. Because of its shape, geometrical reason, if you just roll, it will roll, right? So by somehow, if you can cut sodium chloride in, or rather cut in such a way that you give a shape, sodium chloride a kind of spherical, then it may work. So that was the idea. How do you do that? Because you grow crystal from solvent, you don't have any knife or scissor to actually cut each and every crystal, the way you like. So this is what I have already said, that there are many agents known, but Hindustan Lever told us that you cannot touch this, because we all know how to do that. We want it in a different way, in the geometrical reason. That's what I told you in the previous slide. Now, how can we prepare near spherical salt crystal? You can think this way. Sodium chloride is cubic, as I said, it's a cube. If you cut the edge in the corner of it a little bit, what you end up is called truncated cube. If you keep on doing that, you get cubo-octahedron, and finally you get truncated octahedron. If you do some more, what you get is octahedron. So this particular shape that you are arriving from cube to octahedron is just by cutting the corner of the cube. So if you take the cube, each corner you keep on chopping. You keep on chopping the corner, and finally you end up getting this kind of crystal, octahedron. Octahedron shape we all know. And actually, this is the real octahedron shaped sodium chloride crystal, and first time it was like 1783, it was grown from urine. So it immediately tells you that there are certain elements, certain compounds, which we call additive or impurity, that can have enormous effect on the habit of the growth of a crystal. Some few slides for you. Crystals are beautiful. You see the protein crystal, it looks so nice. This is quartz crystal. This is single crystal. And this is the crystal of gypsum. You can see they are gigantic. You can probably recognize that one person is standing here. You see? So this is somewhere in Mexico. I took this picture from internet. So naturally grown crystal of gypsum. Now, what is a crystal? Many of you who are students in class 11 and 12, you know that crystal is a substance. By definition, it should diffract X-ray. A glass block is not a crystal, although it looks like a crystal, right? It has got a nice shape, it is transparent, it has got all the surface, smooth surface and all, but you won't see any diffraction. So diffraction comes because of the periodicity. So a crystal by definition is periodic. What does it mean? It means that within the crystal, you have the molecule, you have whatever you have, it is made of. They are periodic. What is periodic? Suppose if I consider this particular dias a unit cell. Unit cell is the building block of a crystal. Now if I stand here in this corner, and then if I walk, I will find myself there. If I walk further, in the same unit length, I will again find myself. So this is called periodicity. So if this periodicity is not maintained, X-ray will not be diffracted. You can do this simple experiment at home. I don't have that, otherwise I would have shown you. This is a laser light, right? Consider this X-ray. And you put a piece of net cloth in front of it. Net cloth is a kind of periodic mesh, that we use to prevent insect to come in, right? Moshari, you can use moshari. Take a piece of moshari where you have very small, threads, and switch off the light and shine a laser light on it and see what happens on the wall. You will see nice distribution of spots. And that happens because your light interact with the spacing available with this net cloth or whatever, the piece of motion. That's called diffraction grating. Okay? And that nice spots which are evenly distributed has a particular symmetry. If you have your diffraction grating periodic, ordered, okay, otherwise it will not have it. So crystal is made of unit cell, as you can see, and they are periodic, I have already explained. And this means that, this is periodicity. So if you go 1 unit length in any direction, you should see the same thing. Why I have given you in detail about all this? Because it is very important, because we are going to modify the shape of sodium chloride, which is cube. If I do not know, if I do not know how these crystals are made of, what are the properties, basic properties, I cannot do anything. Now look at the sodium chloride crystal. Sodium chloride is cubic, and if you define sodium chloride, the cubic crystal, in 3 axes, A, B and C, then the plane, which is like, if I say this is A, this is B and this is C, then this plane will be 1, 0, 0, this plane will be 0, 1, 0 and 0, 0, 1 and so on. But if you look at the corner, which I showed in the previous slide, that chop the corner to get the truncated octahedron, and finally you come to the octahedron crystal. This corner is called 1, 1, 1. You probably have read in 11 and 12 the Miller indices. I am not sure though, but if you have read that this, by this particular way, you can actually define the various planes of crystals, and that is important. In this particular slide, you can see that this is the sodium chloride crystal structure. This is sodium and this is chlorine. And if you look at the corner, this corner is made of alternating arrangement of chloride and Na+. The first layer, any layer, you see, this is chloride, and below it is sodium, and then below it is chloride, and so on and so forth. So this is called 1, 1, 1 plane. That is the corner plane. Now, if you look at the edge, if you just look at the edge, this edge is 1, 1, 0. Because this is 1, and this is parallel to C axis, and therefore this is 1, 1, 0. These two planes, also 1, 1, 1, 0, 0 plane, which is this one, are all important planes of sodium chloride. Now, if I have to build a near spherical crystal out of cube, I have demonstrated you that if you take the corner, means if you keep on chopping 1, 1, 1, it gives you a octahedron crystal. Now, if I do the same thing, chopping the edge, that means suppose I take a blade and cut this piece off, then I generate a plane which is 1, 1, 0. And if I do it from all sides, I will be ending with a shape called rhombic dodecahedron. Just close your eyes and think and imagine a cube. A cube has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12 edges. And you keep on chopping that. If you do that, what you are doing, actually you are generating 1, 1, 0 plane, which is this one, from all sides. And that will ultimately give you a shape called rhombic dodecahedron, which is close to a sphere. Okay? And this is how it is possible to convert a cubic crystal to a spherical crystal. And I have already told you why do I need to create a spherical crystal? Because spherical crystal will have a better rolling, and this rolling is directly associated to the free flow of the sodium chloride. So this is 111 and 110. So I have already explained, and here schematically I have shown you that this is 111 plane, this is 010 plane, and this is 110 plane. And this particular plane is important to us. Now, I will show you an animation and a real video of crystal growth, and I will tell you about a saying that we always say in Bengal, that आगे गेले बाघे खाए, पौड़े गेले सोना पाए. What does it mean? आगे गेले बाघे खाए, पौड़े गेले सोना पाए. आगे जे जावे से मारा जाए, जे पौड़े जावे से survive करे. Crystal growth theory is very complicated. I am not an expert to tell you what is the crystal growth theory, but as far as this particular project is concerned, this particular theory is very important. What it means that the plane grows faster, disappears. The plane grows faster, disappears. The plane grows slower, survives. So you have to create a situation somehow 110 plane will be growing